Here in the beginning of 2015, the International Year of Light, I am very happy to be able to present, to be able to talk to you today about the technological advances in lighting. As you know, light-emitting diodes, or LEDs, are being very energy efficient, and they are replacing incandescent and fluorescent lighting all over the place. And you can see some of these lighting installations here in the room today. My name is Carsten Dam-Hansen. I'm a senior scientist at DTU Fotoniks, which is the Department of Photonics Engineering at DTU. Our research group has worked within this area since 2004, and we have established one of the best research, innovation, and characterization laboratories in Northern Europe, looking and focusing at new lighting technologies. Today I will be talking about properties of light-emitting diodes with a special interest in museum lighting applications. So, get this working. So, solid-state lighting, we also call it. That is LED-based lighting. We give it this acronym, SSL. It's the new lighting technology that may offer many advantages, and many of these advantages are very important for museum lighting also. And in museums, we would like to visually present the objects, but light may also destroy fragile objects in museums. So there are several aspects to be considered. And today I will look at the different aspects of light from LED light sources and compare them to traditional light sources. We'll briefly talk about the ultraviolet and infrared light that may cause damages to fragile objects in museums. More importantly, we'll look at the energy efficiency of LED packages, the actual electronic components, and the solid-state lighting products that are produced from the LED packages. What can we expect in energy efficiency, and what can we expect in light quality? And in light quality, we have always been interested in what is the color temperature you can achieve. Does it look warm white or cold white? And what is the color rendering properties of these new light sources? That's of a main interest for museums. Also, the long-term stability is very important. Museums would like the visual appearance of their objects to stay the same over many years and be the same from lamp to lamp. So the maintenance of luminous flux, and especially the color of the light from these light sources, is very important. And I will present some experimental results that we have done on this. Results from two major research and development projects that has been financed by the Danish Energy Agency through Elforsk will be presented here today. And that will lead me to the end, where I'll talk about test and characterization of solid-state lighting products, which is very important these days. So let's start by looking at the non-visual effects of light. Infrared radiation, that is light at longer wavelengths than 780 nanometers. It's light that we can feel the heat from. They may cause surface hardening, discoloration, and cracking of objects. So in 2011, we actually made a new lighting installation at the display cases at the Royal Treasury at Rosenborg. They were formerly illuminated by 5-watt incandescent light bulbs, and they used more than 30 of these incandescent light bulbs in a display case that is using more than 150 watts of electrical power in one display case. And the infrared radiation from these low wattage incandescent light bulbs actually caused the heat to increase by up to 12 degrees in these display cases during a day. So Rosenborg would like to have a new system for this, a system where these things could be avoided. And you can do that by using LED technology. But they would like the visual appearance to be exactly the same as with the old incandescent light bulbs. And for this, we made a totally new color mixing system that produced light with a color distribution looking like this. And actually, the objects would appear the same to the eye. But the change is that we have no infrared radiation from this light source. We only used about 30 watts of electrical power, and there was no measurable change in temperature in the display cases during the day. So this is a very important advantage of LED technology compared to traditional incandescent light sources, halogen or incandescent. UV radiation may, through photochemical actions, may cause color change or loss of strength of the objects in museums. So we usually describe the amount of UV light, that is light with wavelengths below 400 nanometers. We describe that by the amount of UV light in microwatts compared to the amount of visible light that we measure in lumens. So it's a measure in microwatts per lumen. And if you look at daylight, I have a table here showing the UV content of different light sources. And you can see for daylight, we have a very large amount of UV light, up to 1500 microwatts per lumen. And for a tungsten halogen, even with a UV stop, has up to 170 microwatts per lumen. And if you look at LEDs today, I have shown it on this graph over here also. So the tungsten halogen, you can see, has a part of the light that is below 400. And it's up to this 117 microwatts per lumen. But the LED, which you can see the spectral power distribution of here, you can see there's almost no UV light. So the measure is around or less than 5 microwatts per lumen. So that's another very big advantage for LED lighting compared to the traditional light sources. Let's take a look at what are the actual components that we use in these solid-state lighting products. So these are the LED packages. It's surface mount electronic components with very small chips. The chip sizes are around 1 by 1 millimeter. So these packages are maybe 3 by 3 millimeters, 2 millimeters high. And we can run them at very high electrical powers. Up to single chip LEDs can run up to 5 watts of electrical power and deliver up to 1,000 lumens of visible light. And if you compare that to a 60-watt incandescent light source, you would get 700 lumens. So from one of these tiny objects, you can actually get more light than you can get from a 60-watt incandescent light bulb. You can also make arrays of these single chips, so you can have very large arrays that can run at very high powers, even more than 100 watts of electrical power, and you can get very much light from these. With respect to what color temperature or what tone of white light you can achieve from these light sources, I will only look today at white light LEDs. That is blue LEDs that is equipped with a phosphorus material that will convert some of the blue light to red and greenish light, so that we get white light from these LEDs. You can get all different kind of color temperature from these white LEDs. And taking the 60-watt incandescent light bulb again, it has a color temperature around 2700 Kelvin, so that we consider as being warm white light. In LED, we consider the range from up to 3500 Kelvin. We consider that as being warm white. And if we look at the efficiency of these kind of LED packages, then from the data sheets you will get at a specific current, here 350 milliamps, you will get a specific total flux that you can get from this, and you can calculate that to an efficiency. And for these warm white LEDs, you can actually get more than 110 lumens per watt. And if we compare again to the 60 watt incandescent light source, that has an efficiency that is only 12 lumens per watt. So we are more than 10 times higher in efficiency for a warm white LED that produces the same kind of warm white light as the 60 watt incandescent light source today. You might have seen that you can also get LED light that is very cold white, and many people would dislike that. Then the spectral power distribution looks something like this. You have a very pronounced blue peak, and the light actually looks very bluish. So that we call that cold white light. It's characterized by color temperatures more than 5000 Kelvin and corresponds to daylight. The efficiency of these cold white LEDs is even larger. So for these you can get up to 150 lumens per watt. And if you go through the research results, you will find that last year one of the main producers of LED chips in the world, Cree, they produced a continuous running at 1 watt, an LED, white LED, that could supply 303 lumens per watt. So that is a much higher number, and this is just to show you that we are not at a saturated level in efficiency today. So we will see, in the coming years, we will see even more efficient LEDs on the market. But on the market today, if we want warm white LED, we have an efficiency of about 110 lumens per watt, and cold white maybe 150 lumens per watt. But these are the raw LED packages, and these efficiencies are measured at very specific conditions. But if we want a solid-state lighting product that can be used for illumination in this room or in museums, we have to put them in on a PCB. We have to include some optics in order to be able to direct the light where we want it. We need to put some heat sinks in to drive away the excess heat that is produced in the LEDs. And there will have to be some driver electronics. So all these things will produce losses. So we cannot expect the solid-state lighting products on the market to have the high efficiencies that I just showed you for the LED packages. But what we can expect and what we see on the market is that LED lamps that are like this, it could be retrofit lamps with a certain cap. It could be a replacement bulb for a 60 watt incandescent light source like this, giving light in all directions, a non-directional light source, which we call it. They would have efficiencies today around 50 to maybe 100 lumens per watt. So they are still much better than the 60 watt incandescent light bulb that was at 12 lumens per watt. You can get, so these are the retrofit products. We call them LED lamps when they have a cap for a certain installation. You can also have LED luminaires that are ready-made luminaires or spot lamps with all the driver electronics included in it. So you could have spot lamps for this that might be used in museums. You can have troughers to be used in offices, or you see more and more on the streets also street lights based on LED. We will see these everywhere. When describing the light quality, we would actually like to be able to describe the color of the light. And we use the science of colorimetry to do this. In colorimetry, we have defined some color matching functions that actually is just a mathematical description of how our eyes sense the different colors. So we have 3 different colored sensors in our eyes, and they are described by these 3 color matching functions. We'll not get into detail with this, but just show you this chromaticity diagram that shows the color of the perceived light from some specific light source. And this diagram is within this perimetry, we have all the colors that we can perceive with our eyes. And on the perimeter here, starting down here, we have the saturated blue colors. Up here, we have the saturated green, and it goes to the yellow and the reddish. Today, we are interested in white light from LEDs, and white light is concentrated in this area along this Planckian locus, we call it. So it corresponds to a light source, a thermal light source that you heat to a certain temperature. So it could be an incandescent light source. Now I'll just put another color scale here that we use to describe the warm white light. So the warm white light is here near to the reddish end of this chromaticity diagram, and the cold white light is here close to the bluish end. And you see here also the color temperatures of the light. So let's take a closer look. Now I've just taken this area here in the white light area and made a magnification of that. I put a lot of points on that. I'll come back to this. The warm white light is still in this region, and the cold white light is over here. So if you look at daylight from a clear blue sky, you would have a spectral power distribution that looks like this. The chromaticity, or the perceived light, would in this diagram be down here in the cold white range. If we look at the halogen light bulb that we took as an example before, has this smooth spectral power distribution. It has a color temperature around 3000 Kelvin. It will be positioned here. And if we take the example from before, from Rosenborg Castle, the display cases, it used these 5-watt incandescent light source, incandescent bulbs. And the color temperature of these is 2200 K. So it's very, very reddish, warm white compared to the 60-watt incandescent light bulb. So let's see, where are the LEDs in this? So you can get cold white LEDs with this marked blue peak. They all correspond to the daylight spectral power distribution. So you could actually have these 2 spectral power distribution could give the same light impression, but they are actually totally different in the spectral power distribution, and they will render colors differently, but we'll get back to that part of it. You could have something at 3000 K that looks like this. Now the blue peak is less marked, and you have more red light in this, actually saying that you have a better color rendering of the red objects. We'll also come back to that. You can change this. You could have even less blue light from these white LEDs, and you could have warm white that corresponds to this 60-watt incandescent light bulb. And the last example I have here is the color mixed LED light that we made for Rosenborg Castle. It had exactly the same visual appearance as the 5-watt incandescent light bulb. So they would be placed at the same place in this chromaticity diagram, describing the color that we see with our eyes from these light sources. So let's get back to all these points. These are measured chromaticity for a lot of different LED lamps that we took from the Danish commercial market. It was in the years of 2010 to 2011. We measured a lot of these directional LED lamps to be run at 12 watts. A lot of museums were interested in using those kind of light sources because they were using 12-watt halogen light bulbs in many of their exhibitions. So what you see here is that there's a large majority of points here corresponding to 2700 K. So that is warm white light from LED light sources. So, and there's also a lot of products that produce light around 3000, and that is actually more a replacement for halogen light sources. The color difference here shows that the red points have a color rendering that is above 80, so it has a color rendering index of above 80. It could have a color rendering that is even better, but 80 is like a standard for most lighting applications in Denmark. There's a demand that the color rendering index should be larger than 80. For some applications, we would like the color rendering to be even higher, and we mark these products with those that have a color rendering higher than 90 are marked by green. You can see there are some products, so you can get LED products with high color rendering. But one of the things to note here is that some of these green points, even having a very high color rendering index, and should be good white light to be able to differentiate different colors, shades of colors, actually are lying far from what we consider as being white light. So these LED lamps actually has a reddish tint. And if you compare them to a halogen light source, they will seem very reddish. And some people might not think that is very good. Some of these light sources are lying on the other side, on the top side of this Planckian locus, as we call the white light line. They would be on the greenish side. So actually, we need to know from these light sources what color temperature they are, where they are along this line, but we also need to know, are they on the reddish side or are they on the greenish side? Because people will be able to see this tint of light. So, and we scientifically we describe this by a measure that is called DUV. We'll not get further into that. As I said before in this chromaticity diagram, we can easily have two different spectral power distribution that actually produces the same visual appearance, but they will have different color rendering. So here I've taken 3 LED lamps that has the same color temperature. They are all at 3000 Kelvin, corresponding to being able to replace a halogen light source. But they have very different spectral power distributions, as you can see here, and they have very different color rendering. So you can see this top one has a peak which is in the yellow range, and this bottom one has shifted its peak from the yellow actually to the red. So there's much more red light in this lower LED lamp spectral power distribution. And what we do in describing the color rendering, we are actually comparing in this case where we have a color temperature of 3000 K, we're actually comparing with a halogen light source or something very close to a halogen light source. And a halogen light source has a lot of red light, so to be able to give the same color rendering, we need a lot of red light. So that would actually imply that this LED lamp containing a lot of red light would have a high color rendering, and that is the fact also. It has a color rendering index of 95, which is very good. The maximum would be 100, so we're very close to getting the same color rendering as the halogen light source. And the top one has a much lower color rendering, so it's only 69, and it would not be appropriate for many applications. Then there's a large scientific discussion on whether this color rendering index is good enough, and in many cases it's not describing LED light sources in a proper way. But you can do this better by looking at specific color rendering indices. So you can actually look at specifically strong red objects that are unfortunately stroken out by the screen. But the strong red light, you can see a very large change here. So with this LED lamp up here, which has almost no red light, it has a very low -35 of color rendering for red, strong red objects. And this LED lamp down here has a very good of 85. So this is just to say that you can get LED lamps with the color temperature you want, and you can also get a high color rendering if that is what you want. But there's a trade-off here, because this top LED lamp has a much higher efficiency than this bottom one. So, and the change might be 10 to 20%. So if we want this high color rendering, we will get a lower efficiency of this lamp. But for many applications, you would do this trade-off and get the higher color rendering. And you can see this color rendering goes from the general color rendering index goes from 69 to 95, so that's not a large span, but this strong red object actually goes from -35 to 85, so it's a very large span, and that is where you can see the large change in the properties of these LED lamps. As I said, the long-term stability, both of the flux, the amount of light that comes from the light sources, but also the color of the light, must not change in an exhibition. It should be the same over many years. Many of these LED lamps, they actually comes with a lifetime estimate that is maybe 25,000 hours. These many lamps that I showed you the measurements from before, we took 48 of them and put in continuous operation, and we have been running them for 28,000 hours now. So that is almost 3 years of 3 years of continuous operation, just to see what happens with the light from these light sources. And we measured at different time intervals. In the beginning, every 1,000 hours, and then at longer time intervals. But we have a very comprehensive data set for these LED lamps now, and we're going to publish this soon. And I can show you here today already that these lamps, we normalized the initial flux value. So this is the luminous flux measured in lumen, normalized to what it was at the beginning. So beginning at 100. And you can see this blue line and this black line actually shows a very slow decrease of the luminous flux. And actually over this almost, here are data for up to 20,000 hours, it's only decreased by 5 to 6%. So showing this very good stability of the luminous flux of these specific LED lamps. But the red line shows a totally different scenario. Here you can see that the red line, it drops very quickly, and it actually crosses this line. This line is the 70% drop in luminous flux. That is what is usually traditionally used for describing the lifetime or the maintenance of luminous flux. So you would state a luminous flux maintenance time or corresponding lifetime to be around 8,000 hours. And we measured something like 12,000 hours for this. So that is far from the 25,000 hours that many of the producers actually say these these products can do. Now, so you can actually get, if you buy some good products, you can get LEDs that last very long, and the lumen depreciation is very low over these 20,000 hours. But you can also be unfortunate and buy something that will burn out very much earlier. Now let's look at the color maintenance. We would like the color, now let's look at the color temperature. We would like the color temperature to remain the same, so the visual impression of the exhibition is the same over time. So we took these measurements and used the colorimetry to calculate the color temperature, and you can see for the blue and the red line here, we have a very stable. It doesn't change by more than 30 or 40 Kelvin, and you would not be able to see that with your eye. So that is very good for these two LED lamps. However, these other ones that start at 3000 K, you can see the black line, it actually increases in color temperature, and the green line decreases in color temperature. So that is not very good. The black line starts from around 3000 Kelvin and goes to around 3400 Kelvin. So that would easily be visually seeable. So if you put a new lamp and an old lamp together in this exhibition, you would be able to see a large color change, and you are not interested in this. So museums would like to get away from these type of products. You could look at this in a different way. You could use the chromaticity diagram that I showed you before. And here if we take this black line, so we have, in the beginning, we had 3000 Kelvin of white light that corresponds to the halogen light source. And you can see here, it starts off very nicely, exactly on the Planckian locus, what we consider white light, but then it deviates from this, and it moves up to higher color temperatures. And you can see this graph actually contains data from up to 28,000. I didn't have that on the previous graph, but it shows that it's very far from where it started. You can see the red lines here. They're all situated within this small red circle, and the small red circle actually sets the distance for where we could see a visible difference. So if it is within one circle here, we will not be able to see a visible difference. So this red LED lamp producing these LED red points on the graph would be a very good LED lamp for this. So this leads us to the test and characterization. You can see there are many of these issues with LED lamps that needs to be measured. It's not like traditional light sources. A halogen light source, we would know on beforehand what the spectral power distribution was, because it's determined by the physics. But LED lamps can be made in so many different variations, in color temperature, in color rendering, different spectral power distribution. So we actually need to be able to measure all these characteristics of LED lamps and LED components. So at DTU Fotoniks, actually at Risø campus, we have developed a totally new photometric lab that contains large integrating spheres and a large gonio-photometer that can take lamps up to 2 meters in largest dimension and we're able to measure the spectral power distribution. We need to do that in order to calculate all these things. We can measure the total luminous flux, the electrical power, which gives us the efficiency in lumens per watt. We can measure the intensity and color as a function of angle. So for many applications, you need to know, as an architect, you need to know what is the distribution of light, and then you can put that into a simulation calculation to see if you get light where you want it. From all these measurements are based on that we measure actually the spectral power distribution. So we use spectral radiometers in all these setups. We have spectral radiometers that are very accurate, that are used in the lab. We also have some handheld spectrometers like this one today here, where we can take that to any installation, to a museum, to show them what they actually have on site. And from all these spectral measurements, we can calculate the color temperature, we can calculate the color rendering index. And from lab measurements, we have the luminous flux and color maintenance. And specific things like relative damage factor is important for museums, and that takes into account the UV and the infrared radiation. So we need to be able to measure UV light and infrared light also. And from many of these handheld spectrometers, you cannot do this. And in the lab, we have special double monochromators that are especially designed to be able to measure in a very large and very accurately in a very large wavelength range. When you run a test and characterization lab like this, you need to be sure that it's calibrated and that you get accurate results from your measurements. It's all based on accurate calibrations, so we calibrate all our instruments. So that might be a bit strange in a university to have absolute measurements, but we run this test and characterization lab both as a commercial lab and as a research lab. So it's also open for students that would like to come and do measurements. But we also do commercial measurements for industrial companies that are making lighting products. But we need to make sure that we do measurements as all other labs in the world. And I've been working under the International Energy Agency in the Solid State Lighting Annex. It has been running since 2010. It's an organization that wants to help the governments ensure that the solid state lighting LED products on the markets today actually are good enough and that they have high energy efficiencies. This is continuing to 2019, and we're involved in this. And in 2013, we made a comparison of 110 laboratories measuring the same lamps. And actually, this shows a very good agreement between the different labs. Here you can see the measured luminous flux of these 110 labs, and they are all within plus minus 4%, which is very good for photometry. So I've given you a lot of information on solid state lighting, that is LED-based lighting, which is a new lighting technology that for museum lighting actually offers a lot of advantages. Limited UV and infrared radiation, very high energy efficiency, high light quality. We can choose the color temperature and color rendering that we want. They have long lifetime. They may give color tunability. I haven't discussed that. And dimming should be, but might not always be easy. But there's still a need to test and characterize all these products. So I would like to thank you all for listening today. I would like to thank all my co-workers at the LED team at DTU Fotoniks and for your kind attention.